All right, coming back now, we left off doing electron configurations and orbital diagrams. The orbital diagrams, again, are useful because it can help you decide whether there are any unpaired electrons in an atom, which can affect the magnetic properties of the element. Where we pick up is with the idea of valence electrons. I've mentioned, oops, sorry, down a little bit. There we go. I've mentioned that before, and how valence electrons are important because they determine the kinds of compounds a compound will form and the kinds of things that the compound will react with. And to some extent, even the kinds of bonds that the compound will form with other elements are determined by the valence electrons. And so the number of valence electrons is actually, actually turned out to be part of the way that the periodic table is arranged. They didn't know it at the time, but when they placed elements or elements with similar properties together, they were also effectively placing elements with similar electron configurations together, although they didn't even know about electrons yet at that time. Turns out the electrons are responsible for most of the properties of chemical properties anyway of an element. And specifically the electrons that are responsible for the chemical properties of the elements are the valence electrons. The valence electrons, again, are the electrons in the outermost principal energy level, or the outermost shell of electrons. And effectively, whenever two atoms come together to try to react with each other, all they see of the other element will be the valence shell electrons. The inner electrons, anything below the valence shell, are completely sort of cut off from the outside by the valence shell. So anytime a reaction occurs, anytime a bond is formed, it involves the valence electrons of the atom and only the valence electrons of the atom. So the valence electrons are very important. Okay, they're involved in responsible. Okay, for the main group elements, that is the A group elements, the group number, at least according to the AB system of numbering the groups, is the number of valence electrons. So, sodium is in group 1. Sodium has 1 valence electron. Silicon is in group 4A, and so silicon has 4 valence electrons. And all of that is true. The B groups are a little harder to predict, and so their number of valence electrons do not correspond to the group number. But for the A groups, they do correspond. Okay, so for sodium, we saw the electron configuration for sodium just a moment ago. 1s2, 2s2, 2p6, 3s1. The valence shell is all of the electrons with the highest principal quantum number. So in this case, that would just be that single s electron in the third shell. So sodium has 1 valence electron, and that's why it's in group 1A. For neon, as we saw right before sodium, the valence shell is all of the electrons with n equals 2. And so you have to watch out, because the tendency might be just to look at the last electrons in an electron configuration and say, oh, neon's got 6, it should be in group 6. No, it has 8 2 plus 6 electrons in the valence shell, and therefore it's in group 8A. Fluorine has a valence shell electron configuration of 2s2, 2p5. That's a total of 7 valence electrons, 5 plus 2. And so fluorine is in group 7A. Oxygen has, as we saw a couple of minutes ago, has a valence electron configuration of 2s2, 2p6. Sorry. 2s2, 2p4. And that's a total of 6 electrons in the valence shell. And that's why oxygen is in group 6A. Nitrogen has a valence electron configuration of 2s2, 2p3. That's 5 electrons total in the valence shell, and that's why nitrogen is in group 5. Boron, let's see, carbon, 2s2, 2p2, that's 2 plus 2 or 4 valence electrons. Carbon's in group 4, and so on down the line. Helium, as I mentioned a moment ago, has 2 valence electrons, because that's the only electrons it's got in that case, and it's in group 8. Now, they might think that's weird. Why isn't it in group 2? They decided to put helium in group 8 because the 2 electrons in the valence shell actually fill that valence shell. Because in this case, the valence shell is the first shell, the only shell. And the fact that the valence shell is filled makes helium very stable. And so most of its chemical properties are actually closer to those of the noble gases. All of the other noble gases have 8 electrons in their valence shell, though, like neon does. And so helium is a bit of an anomaly. It's in group 8 because it acts like it's in group 8, even though it really only has 2 valence electrons. So that's something that we kind of have to keep in mind about that. Now, a shortcut to doing electron configurations can be using the symbol for the last previous noble gas to represent the electrons up to that point. Because, well, due to the Aufbau principle, the only differences in ground state electron configurations between elements is in the valence shell. The inner shells, the core electrons, in other words, are the same for any given element in a given period. And so this brings us to the idea of noble gas abbreviations. So you can use the symbol of the last previous noble gas in square brackets. The square brackets around the symbol for the element are what sort of denote electron configuration to symbolize the electron configuration of that noble gas. And that would also be the core electron configuration of all of the elements that come after it up until the next noble gas. And you can just use the symbol for the noble gas to represent the electron configuration of the noble gas. And then for the element you're interested in, just add the electrons that it has beyond those of the last previous noble gas. So like I was showing just a moment ago, neon has, well, let's see, fluorine, let's put it like this. Fluorine has a configuration of 1s2, 2s2, 2p5. Well, 1s2 happens to be the electron configuration for helium. Whoops, say helium. So you could represent the electron configuration for fluorine as helium in square brackets, followed by whatever fluorine has beyond what helium has, which is 2s2, 2p5. That would be another way of representing the electron configuration for fluorine. For sodium, remember we noticed that sodium has 1 electron beyond neon. So notice 1s2, 1s2, 2s2, 2s2, 2p6, 2p6. All of this is the same as the electron configuration for neon. So what you could do instead of writing all of this is put Ne in square brackets and then write what sodium has beyond neon, which is 3s1. So square brackets with Ne followed by 3s1. That would be sodium. Okay, so just as showing some examples here, helium, as we said just a moment ago, has a configuration of 1s2. Lithium has a configuration of 1s2, 2s1. Well, the 1s2 is the same as helium, so you could actually write this as He in square brackets 2s1. Now, you don't really save a lot of work by doing that in the case of these smaller elements. So, and beryllium would be equivalent to 1s2, 2s2, or in other words, helium in brackets 2s2. And boron would be equivalent to helium 2s2, 2p1, because that's what beryllium has beyond what helium has. As you go down the periodic table and the electron configurations get longer and longer, you can save more and more work by doing this. just so without going into really long examples. But for instance, neon, which is atomic number 10 right here in the periodic table, has the electron configuration, as we saw a moment ago, of 1s2, 2s2, 2p6. Okay. Sodium has one electron beyond that. So sodium's electron configuration is 1s2, 2s2, 2p6, 3s1. Well, you can save yourself a bit of work by just writing neon in square brackets followed by 3s1. That means that what sodium has beyond what neon has is 3s1. So if you have the electron configuration of neon and you want sodium, you add one electron, and that electron is in the s block, so it must be an s-type electron. Sodium is the first element in the s block for period number 3, so it must be a single 3s electron, or in other words, the sodium electron configuration ends in 3s1. Magnesium is two atomic numbers beyond neon. So it would have a configuration of 1s2, 2s2, 2p6, 3s2. But of course, the underlined part is just the configuration of neon. So you could also write it as Ne in square brackets followed by 3s2. Aluminum has a configuration of 1s2, 2s2, 2p6, 3s2, 3p1. But of course, the part underlined here is the electron configuration of neon. So you could also represent aluminum as Ne in square brackets, 3s2, 3p1, which can save you a bit of work. Okay, figure 629 in the textbook is a copy of the periodic table, and it gives the end of the electron configuration for all of the elements in the periodic table. And what I mean by the end of it is that they basically give you the electron configuration for the element beyond the configuration for the last noble gas. So if you want the electron configuration from figure 629, you would just take what's written there, but be sure to put in front of it the symbol for the last previous noble gas in square brackets. So again, if you're looking at aluminum, it would say in the little square in figure 629 for aluminum, it would say 3s2, 3p1. But in addition to that, you would have to specify the last previous noble gas, which is neon. Okay, so Ne in brackets, 3s2, 3p1. And that's the way it works for each of the elements in figure 629. And that's why, for instance, cesium in figure 629 is just listed as 6s1. That means that's how the electron configuration for cesium ends. But what would come right before that would be the electron configuration for xenon, which you can represent by Xe in square brackets, 6s1. So you see there's xenon, and here's cesium. So you have the electron configuration of xenon plus 6s1, which makes sense because cesium is in period 6, and it's the first element into the s block. So there should be a single s electron in n equals 6, and 6s1 is indeed how it ends. There are some anomalies in orbital filling. Even if you get the orbitals in the right order, there can still be some anomalies in the way the electrons go into the individual orbitals of a given type. So, of course, there are always exceptions, and then there are exceptions to the exceptions, to the exceptions, to the exceptions. So, just looking at some of these electron configurations here. For argon, it's atomic number 18, and therefore it needs 18 electrons. And if you fill it according to the Aufbau principle, you end up with an electron configuration of 1s2, 2s2, 2p6, 3s2, 3p6. Okay. The outermost shell, that is n equals 3, is completely filled with electrons, and therefore argon is relatively stable, and that's how it gets to be one of the noble gases. Also notice that the third shell has 2 + 6 or 8 electrons. And again, therefore, it's in group 8A. Potassium has atomic number 19. That would have 1 additional electron beyond 3p6. And according to our orbital filling diagram, the next electrons would be 4s1, not 3d electrons. You can also get that order right from the periodic table. Say if you're at argon and you want to know the electron configuration of potassium, well, it's going to be argon plus whatever potassium has beyond argon. And what potassium has beyond argon would be 1 single electron in the s-type orbital, because this is the s block, of shell number 4. So the configuration for potassium should be argon, Ar in brackets, 4s1. And that is exactly what it is. You don't start getting d electrons, remember, until you get over to scandium. And they would be 3d electrons. That's because 4s fills before 3d. And you can get that again just from the arrangement of the periodic table. Calcium has an atomic number of 20, which means it has 2 electrons beyond argon. And so that would be the argon configuration plus 4s2, because calcium is the second element in the s block of n = 4. So for s1, 4s2. Scandium, for an atomic number of 21, has 3 electrons beyond argon. So you'd have argon, and you need 3 more electrons. So you have argon 4s1, argon 4s2, and the next, now we're in the d block, but remember the d electrons would be for n equals, or n minus 1. So you'd have argon 4s1, 4s2, 3d1 for scandium. And then it goes across d1, d2, d3, and so on until you get to 3d10 for zinc. And only then do you start filling the 4p orbitals with gallium. Gallium would be argon 4s2, 3d10, 4p1. And again, you can see that just from the periodic table. Okay, and then gallium, like I said, argon 4s2, 3d10, 4p1. So if we have a question, say, what is the electron configuration of sulfur? This is a little bit different from the example that's in the book for 6.1, because I wanted to show you something a little different, because they explain what they did there. And I did something useful. Going to sulfur, I believe what they had was phosphorus. Going to sulfur adds a little interesting twist that can remind us of something that's important. So we'll see what that is in a minute. So what are the 4 quantum numbers for the last electron added? Well, if the atomic number is 16, that means there must be a total of 16 electrons in the atom. From its position in the periodic table, you can tell a lot about it. Sulfur is right here. It's in period 3. So we know that the electron configuration would end with 3 something. It's also the 4th element in the p block. So we know that the electron configuration should end in 3p4, because it would be 3p1, 2, 3, 4, 3p4. And before that would be 3s2, and before that would be 2p6 for these 6 electrons here, 2p2 for these, and then 1s2 for helium and hydrogen. Okay, so we can tell the valence shell must be number 3. It's the 4th element from the left in the p blocks, so there must be 4 electrons in the p orbitals of n = 3. So the electron configuration ends in 3p4. The full electron configuration from the Aufbau principle would come out to be 1s2, 2s2, 2p6, 3s2, 3p4, because that's the point where you run out of electrons. Or you could also write that as neon 3s2, 3p4, because again, the 1s2, 2s2, 2p6, that is equivalent to neon. And again, you can get that from the periodic table just by looking at where sulfur is and saying, okay, what is the last previous noble gas in terms of atomic number? That would be neon. So it's neon plus whatever sulfur has in addition to neon. And what sulfur has in addition to neon would be 3s2, 3p1, 2, 3, 4. So you can come up with that just by looking at the periodic table. You don't even have to sit down and count out the electrons by the Aufbau method. The sorry. Now, the orbital diagram would look like this. 1s is filled, 2s is filled, the 2p orbitals are filled, the 3s orbital is filled. We've got 4 electrons in the 3p orbitals, so you'll get 3 of them, the first 3 going in singly, and the 4th one pairs up with one of the single electrons that was already there. So that one is the last one to enter, the one that I drew here pointing downward in the left-hand p orbital. So the quantum numbers for that last electron would be n equals 3, because it's in shell number 3, L equals 1, because it's in a p-type orbital, M sub L equals -1, because I drew it in the p orbital on the left, and M sub S equals -1/2, because I drew it pointing downward. Okay, so that shouldn't be too bad. You can also identify an element from its electron configuration. There are actually a couple different ways you could do that. One way is by looking at the periodic table and seeing what basically what the element has in terms of electrons beyond the last previous noble gas. So if we have an element with the configuration argon 4s2 3d5, well, what you can do is look at the periodic table and say, okay, here's argon. In addition to argon, we have 4s2, which would be these two right here. And then 3d5 would take you 5 spaces into the D block. 1, 2, 3, 4, 5. So it's manganese. That's one way to do it. The other way you could do it is just by adding up the electrons. Argon has 18 electrons of its own, plus you have the 2 electrons in the 4s orbitals, plus the 5 electrons in the 3d orbitals. So that's 18 plus 2 plus 5, which is 25 electrons. So we're looking for atomic number 25. And that happens to be manganese. If we had an element with the configuration krypton, followed by 5s2, 4d10, 5p6. Well, again, we could start with krypton, which is right here. And then in addition to that, we had 5s2, so that's these two here. Then 4d10, that takes us all the way across the D block. And then 4p6. So here's the P block of, sorry, 5p6. The D block of shell number 5, and we have 6 electrons in that, so that's 1, 2, 3, 4, 5, 6. Oh, it's another noble gas. It's xenon. Okay, so xenon it is. Again, you could also just add up the electrons. Krypton has 36 electrons of its own. In addition to that, we have 2 plus 10 plus 6. So 36 plus 2 plus 10 plus 6 is 54. And atomic number 54 is xenon. So that's the other way to do it. So whichever way makes sense, you can do it that way. In fact, you should probably practice doing it both ways, but ultimately you can use whichever method makes more sense. And of course, there in chemistry, actually, before I get into that, why don't I cut here, because we're just about 25 minutes in and the first segment ran long. So I'm gonna cut it off here, and then we'll get into this more anomalies on top of anomalies in the next segment. Gives you something to look forward to.